Welcome to this lecture. This is the final lecture of week 1. In this lecture, we are going to discuss some problems and exercises based on the material that has been covered in week 1. So, without further delay, let us discuss through the lecture notes. So, we go back to exercise 1. So, here we are looking at a function defined on the real line given by this formula, that for every real number small x, we are looking at this number 1 by 1 plus x squared, and we want to check the integrability of this function, and the problem statement suggests that we need to show that this function is in L1. Recall this measure space, that together with the real line we are putting the Borel sigma field and looking at the Lebesgue measure. Now, as per our standard shorthand notation that we adopt, we are looking at this L1 of R space. So, we will hide this Lebesgue measure and the Borel sigma field, because this is understood from the context. Now, the function that we are looking at, we want to check the L1 integrability of that. So, first of all, we want to check the Riemann integration structure for this given function. Note that this is a nice continuous function, and moreover we are having this interesting property that x mapping to 1 by 1 plus x squared is an even function. So, therefore, if we are computing the integration of this function from minus infinity to plus infinity in the Riemann integration sense, we will end up with 2 times the integration from 0 to infinity of the same function's integration. But now, let us try to simplify this further. So, here we use this very standard transformation technique, that we change the variable small x to tan theta. So, then the range of theta that we shall end up with will be from 0 to pi by 2. So, therefore, if we do the calculations, we will end up with this value, and the simplification ends up with pi. So, therefore, what we ended up showing is that the Riemann integration for this function can be computed, which turns out to be pi. But now, this function is also a non-negative function. Now, since its Riemann integration exists, we go back to our earlier understanding of the connection between Riemann and Lebesgue integration, and claim that if we were to perform the Lebesgue integration for this function mod of 1 by 1 plus x squared, then first of all, since this function is non-negative, there is no need to keep the modulus symbol. Moreover, since the Riemann integration exists, it will match with the actual value of the Lebesgue integration. So, we can just go back to that value pi that we have found by the Riemann integration, and we can conclude that the Lebesgue integration will also end up having the value pi. Now, this is a finite quantity, and therefore, our claim is that the given function that we are using has to be L1 function. Moreover, the L1 integration, remember, this is exactly the integration of minus infinity to plus infinity mod f d lambda. So, we look at this integration for the function f with respect to the Lebesgue measure, and for the L1 integrability, what we needed to check was that this integration should have been finite, which we exactly computed to be the value pi. So, therefore, the L1 norm of the function turns out to be pi, and moreover the function becomes in L1, it is an element of L1. Moreover, we actually observe further that if we choose a real number p greater or equals to 1, then 1 by 1 plus x squared, that quantity is a number below 1 for all x, less or equals to 1 for all x, and as a consequence, what you can conclude is that raised to the power p, that quantity will be less or equal to 1 by 1 plus x squared. And hence, as a consequence, what we have is that the integration of this function raised to the power p, so modulus included, but these functions are already non-negative, as we have already commented. So, there is no need to separately write the modulus, but we keep it just to match it with our definition of LP integrability. Now, if we were to compute this raised to the power p and with respect to the Lebesgue measure, then that quantity will be less or equal to the function's integration with only 1 by 1 plus x squared without any extra additional power, and that we have already shown to be finite, and therefore, what we conclude is that the given function is actually also in LP for all p between 1 and infinity, 1 included, infinity excluded. Now, with this idea we can also try to ask what happens for p equals to infinity. Now, here we observe that for all points x, the function value is less or equals to 1, and hence we conclude that the function is actually also in L infinity. Just to clarify this point, that the function first of all is a non-negative function. So, when we are looking at the essential supremum of the mod f function, we are actually looking at the essential supremum of the original function itself, because of the non-negative values of the function. Moreover, the function itself is dominated from above by 1, and hence the L infinity bound that we need to establish follows. So, therefore, the function that we are working with actually falls in all LP spaces for p between 1 and infinity, 1 and infinity both are included. So, this gives us some ideas involving the type of functions that are there in the LP spaces. All right. So, let us look at the similar situation involving random variables, and we go to discuss the exercise number 2. So, here our idea is that we are going to look at the random variable which is identical equal to 1 defined on some probability space omega f p. Now, here this constant random variable, we do not need to separately talk about any measurability properties, it is already given to us, but we need to check the appropriate integrability properties. Now, let us fix again a number p between 1 and infinity, 1 included, infinity excluded. Then what happens is that expected mod x raised to the power p, that is just nothing but this integration. So, let us compute this. So, the random variable takes the value 1 throughout. So, we just plug that value in, and that just turns out to be the probability of the whole set omega, which is given to be 1 due to the fact that p is a probability measure. Therefore, all these integral values of mod x to the power p, that becomes 1 for all possible values of p as we considered here, and therefore, x must be in LP, and moreover this quantity is actually equal to 1. Moreover, as argued in the earlier discussion involving exercise 1, we can also check the L infinity bounds. So, here again the random variable is again given to be non-negative, and if we look at the essential supremum of this function mod x, so that is nothing but the essential supremum of the original function x, because the function is taking non-negative values. Moreover, that is exactly taking the value 1, and therefore, we can actually again show that the L infinity bound is finite. Moreover, we can exactly compute it to be the number 1. So, now we have some examples of L infinity functions, LP functions, and similar situations for random variables, LP functions and L infinity functions. Moreover, using other algebraic properties that we have discussed in terms of linearity and other properties, we can also construct other interesting examples of these LP functions or LP random variables. Okay. So, let us discuss some other interesting exercises, but before that we need to recall some concepts from metric spaces. So, these are certain basic facts about metric spaces, and if you are not familiar with these concepts, I would request you to go back and check it from your advanced reanalysis textbooks. So, here what we do is that given any non-empty set capital A, we can talk about a distance function defined on that set. So, to do this, what we work with is a function of the form, it is a real valued function defined on A cross A. So, for any pair of points in the set capital A, we will assign a real number, but with certain properties. So, the properties that we are looking for are like this, that the function assigns value 0 if and only if the points that we are using here are equal. Okay. So, therefore, if two points are equal, we will think of that distance between the points is actually as 0, because it is the same point. On the other hand, if the distance is 0, then we are actually having one point. So, moreover, we should also try to distinguish points by this distance function. So, if x is not equal to y, the distance should be positive. Moreover, the distance from x and y should be the same as distance from y and x. So, this is another expected property, and this is also called the symmetry property for this function. And finally, we also go back to the triangle inequality for a distance function. The triangle inequality says that if you have 3 points x, y and z coming from that set, then if we look at the line segment joining x and y, so this is given, this is the length of that should be less or equal to the line segment's length from x to z and z to y. So, this is essentially talking about triangle involving the 3 points x, y and z, and what we are saying is that length of one side should be less or equals to the addition of the length of the other two sides. So, that is essentially what we call as a triangle inequality. Now, if you have a function defined on A cross A with these properties, then we will call such a function on a set A to be a metric, okay, and this essentially gives us a notion of distance between points on the set. Now, once you have the distance through this metric, then given any epsilon positive, we can also talk about the neighborhoods of these points. So, for example, given any epsilon, we can talk about a epsilon neighborhood. So, it is given like this. So, we can look at all points y such that the distance from a given point small x is less than epsilon, and that set of points we can think of as the epsilon neighborhood of the given point small x. So, here you note that the point small x is already included because the distance from itself is always 0. So, that will also satisfy this inequality no matter what is your value of epsilon. Epsilon is always chosen to be positive, and therefore, x is always there, and we can always ask what are other points y which are included in this epsilon neighborhoods. But once we understand these neighborhoods, we can further discuss the topology on this non-empty set, and the topology is essentially described by the collection of all open sets. Now, again, what are all the open sets? It is that for each point inside such open set, we should have a neighborhood which is completely contained inside the set. So, that is the notion of open sets that we again extend from what is our understanding on the real line. Now, again, once you have the ideas of open sets and certain distances, we can actually talk about convergences as we do on the real line side. Now, here let us quickly describe the notion of convergence in the metric spaces, but recall in the real line we have a given distance function given by the usual modulus functions, but now we are going to use the given metric. So, we say a sequence x n of points coming from a metric space together with this metric D converges to another point inside the set if given any epsilon positive, there exists some natural number capital N such that after that stage capital N, all the points from the sequence are close to x by this distance. Okay. So, therefore, all these points x n falls in the epsilon neighborhood of the point x. So, therefore, that is the notion of convergence which we extend from the real line that we have already seen earlier. The only change that we make is that instead of the modulus distance that we use in the real line, we are using the given distance function D. And similar to the discussion that we perform in the real line, we can also talk about Cauchy sequences, but again using this new notion of distances. So, what we do is that given any sequence in this metric space, so together with this metric, we will say that it is Cauchy if given any epsilon positive, there exists a natural number capital N such that after that stage capital N, all the terms in the sequence are close together and closer by this distance epsilon. So, that is the idea that after a certain stage, all the terms in the sequence are very close together. So, that is the notion of Cauchy sequences. Now, we now discuss the solutions to exercise 5, which asks about a specific property of convergent sequences in a metric space, and the property is that all these convergent sequences must be Cauchy. So, to show this, we repeat the type of arguments that we talk about for real valued sequences. So, here also if you have a sequence of points coming from a metric space and suppose it is given to be convergent to a point small x, then given any arbitrarily fixed epsilon positive, there exists a natural number such that the terms in the sequence should be close to the limit value small x by this distance. So, here you note that since this epsilon is arbitrary, epsilon by 2 is also arbitrarily chosen and it is also a small number. So, given this epsilon by 2, we can figure out this number capital N by the definition of convergence. But now, given that number capital N, we make this observation that for all terms after that stage capital N, if you look at the distance between the terms, we apply the triangle inequality which we discussed a few minutes ago, and we will see that distance between any two terms can be dominated by the distance of the nth term from x with the mth term from x. So, if you add up these two quantities, then that quantity is an upper bound for the distance between the nth term and the mth term. But since the sequence is convergent to small x, then we are having this bound after that number capital N, and hence given that epsilon positive, we have managed to show that all the terms after this stage capital N are close together and closure by the distance epsilon, which we prefixed earlier. But since this epsilon is arbitrary, we conclude that this convergent sequence must be Cauchy. So, here again I repeat that we have essentially repeated the argument that we see for real valued sequences, and the same arguments goes through for the situation involving metric spaces. Now, here interesting comment that we have actually seen earlier, but we will re-emphasize this in the situation of metric spaces. This is about the completeness structure. So, we say a metric space A together with this distance the metric D is complete if all Cauchy sequences in this set converge inside the set. Remember, it is this kind of a property is true on the real line, meaning if you take a real valued sequence and if such sequences are Cauchy, then they must converge. So, we want to talk about a similar property for general metric spaces, and we refer to such properties as a completeness of this metric space. Now, recall earlier that we have shown that if you look at these LP spaces, then there is a natural norm induced in it. So, LP spaces are normed linear spaces, but these norms actually give you a nice distance function. So, to discuss that, we introduce this distance function d subscript p. So, what it does is that given any two functions in LP, you look at the LP norm of f minus g. Remember first that LP spaces are linear spaces. So, given any two functions f and g, f minus g is also in LP. So, we can talk about this quantity. So, this distance is well defined. Moreover, the norm is always non-negative and it will satisfy all the required properties of a metric as required as per the definition of a metric. So, once you have this metric, you can talk about the topology on this LP spaces, and what we have actually shown earlier is that for any such p between 1 and infinity, 1 included and infinity is also included, this space is actually complete. So, we had shown earlier that all Cauchy sequences on these LP spaces are convergent, and there we had used that norm, but we are actually using the distance function arising from the norm, which is giving us this metric structure. So, therefore, we have that these spaces LP together with this metric actually is a complete metric space. Moreover, of course, these LP spaces have the linearity structures, and that is where we end up with this complete norm linear space structure, which is a Banach space structure. But we can also look at the metric space structure and it also turns out to be complete. These observations involving LP spaces have this nice extension involving certain connections with dual spaces. So, remember that we have discussed earlier that for p between 1 and infinity, both 1 and infinity excluded, we can talk about the dual spaces of LP and we can identify them as certain LQ spaces, where Q is such that 1 by P plus 1 by Q is 1. We have also commented on the fact that the dual of L 1 can be identified as L infinity. So, in regard to that comment, we give some additional motivation. So, here we start with a function in L infinity space on some appropriate measure space omega f mu. So, again for shorthand notation we just write the measure. Now, since f is in L infinity, then for any constant greater than this L infinity norm, we have that modulus of f must be less equal to such a constant c almost everywhere. But then what you get is that given any other function g coming from the L 1 space, the modulus of f g is less or equals to c times modulus of g. This happens almost everywhere, and therefore, we can talk about the integrability of f times g. So, the L 1 norm of f g, which is the integral of mod of f g, that can be dominated by this constant times mod g, all right, and that is actually the L 1 norm of g. So, we have that the L 1 norm of f times g is dominated from above by c times L 1 norm of g, and that is given to be finite. So, therefore, f times g is actually is a L 1 function. So, what we have actually shown is that if f is in L infinity and g is in L 1, we actually have f times g is in L 1, and the integral of that will give you a certain number that is dominated by this bound. But now, we can also strengthen this bound by varying this constant c greater than L infinity norm of f, and if you vary all this c, we can take the smallest such c. Going back to the definition of L infinity norm, we end up with this bound that L 1 norm of f times g is actually less or equals to L infinity norm of f times the L 1 norm of g. So, this is essentially hinting to the duality structure from L 1 to L infinity. Moreover, we can restate all these results in terms of random variables also. So, here what we do is that if you take any L infinity random variable x and the L 1 random variable y, then the same kind of bounds will read as follows, that x times y must be again in L 1. So, that is the first statement, and moreover the L 1 norm of x times y is less or equals to the product of the L infinity norm of x and L 1 norm of y. So, a final comment before we stop is this, that if x is a L infinity function, then whenever you choose a constant greater than the L infinity norm, you will have that mod of x is less or equals to a constant, right. So, we can strictly speaking we can put a term almost surely here, but for all practical purposes when we are looking at the integration of x or mod of x, this is the bound which we refer to. Now, here we immediately will end up having the fact that expected value of mod of x is again less or equals to this constant. So, now again we can appeal to the similar argument that we discussed earlier. We will vary all such c greater than the L infinity norm of x, and we end up with the fact that the L 1 norm of x is less or equals to the L infinity norm of x. So, here the L 1 norm is nothing but this expected value of mod of x. Now, once we observe that, what we ended up having is that the L infinity random variables are also L 1 random variables, and therefore, this inclusion follows. Moreover, this is not only restricted to the situation of L infinity and L 1. More generally, what we can actually show is that L infinity space actually is contained in LP space for all p between 1 and infinity, 1 included, infinity excluded. So, here we note that we are only talking about the probability measure p, and this kind of inclusions in general measures may not be true. So, when we are using the probability measures or more generally finite measures, these kind of inequalities will continue to hold with appropriate modifications, and the set inclusions that we see here will be true. But infinite measures, this kind of set inclusions may not be true. All right. But in this case of probability measures, what we will end up having is that again the LP norm of x can be dominated by the L infinity norm of x. So, again we end up having this kind of nice inclusions. Moreover, we can get further nice results from these inequalities. So, we observe that if x n converges to x in the L infinity norm, then the L infinity norm of these quantities goes to 0 as n goes to infinity. But as we have already shown that the LP norms are less equals to the L infinity norms, therefore, what we have is that these quantities are actually again going to 0 as n goes to infinity. So, therefore, if you have that a sequence of random variables converge to x in the L infinity norm, they also converge in the space LP. So, therefore, this is essentially extending the property that if you have p less than q, then LP convergence is implied. So, LP convergence can be implied from LQ convergence. So, control of the higher norm in terms of the q norm or in terms of the random variables the higher moments, that is always giving more information, and that is what is helping us prove the appropriate convergences or appropriate inequalities. So, this kind of results hopefully will help you understand the content of this week. We will continue the discussions involving such kind of LP spaces in the next week's lectures. Thank you.